output. Equation A will provide the first n by 2 samples of the endpoint DFT output because the value of k can be from 0 to n by 2 minus 1. So the range of k is n by 2 samples for all these equations, while the remaining or the last n by 2 samples of the endpoint DFT output can be obtained through equation B. And the working of both equations are exactly same as you can see here. In both equations, we are combining or we are adding n by 2 point DFT outputs. But during this combination, we have to multiply the second n by 2 point DFT outputs with some total factors, as you can see in both equations. So the thing to remember is that first n by 2 point DFT outputs will appear as it is during addition, while the second n by 2 point DFT outputs will be multiplied with these constants, which are so-called total factors. And in a more compact form, we can write equation A and B like equation 1 and 2. If you'll call the first n by 2 point DFT as A of k is representing the first n by 2 point DFT output, while the second n by 2 point DFT output is represented by B of k. So equation A will become equation 1. Similarly, equation B can be written as equation 2. Now, in order to understand these equations in more detail, we can assume a value of n is equal to 8. So when we will put n is equal to 8, then the range of k will become 0 to 3. So let's put capital N is equal to 8 and k is equal to 0 to 3 in equation 1. And just imagine what will happen. Equation 1 will provide the contribution of capital X of 0, 1, 2, 3. By combining 4-point DFT outputs, the first 4-point DFT output is A of k and the second 4-point DFT output is B of k. So we will need to add A of 0 with B of 0, but before addition we have to multiply B of 0 sample with W8 0 factor. Similarly, X of 1 can be calculated by adding or combining A of 1 and B of 1. Now what is A of 1 and B of 1? A of 1 will represent the second sample of the 4-point DFT output. Similarly, B of 1 will represent the second sample of the second 4-point DFT output. But before this addition, we have to multiply B of 1 sample with W8 of 1. Similarly, you can calculate X of 2 and X of 3 in a very similar way. So the conclusion is we will add first 4-point DFT outputs with the second 4-point DFT outputs, but during this addition, the second 4-point DFT outputs, which are represented by B of k, will be multiplied with these constants, which are W80, W81, W82 and W83. So this equation 1 will provide the first 4 samples of the overall 8-point DFT output. Similar is the case for equation 2, when we will put n is equal to 8 and k is equal to 0, 1, 2, 3. Then we will get the contribution of X of 4, X of 5, X of 6 and X of 7. And for the calculation of these components, again we are going to add first 4-point DFT outputs with the second 4-point DFT outputs, which are represented by A of k and B of k, which will be simply A of 0, A of 1, A of 2, A of 3 and B of 0, B of 1, B of 2, B of 3. So in order to calculate X of 4, we will put k is equal to 0 in this equation and n is equal to 8. So X of 4 will be equal to A of 0 plus B of 0, but B of 0 will be multiplied with W8 of 4 before addition. Similarly, we can find X of 5, X of 6 and X of 7 in a very similar way. So equation B will provide the last or the remaining n by 2 samples of the overall n-point DFT output. So this was the summary of the previous lecture. In this lecture, we will see how we can implement FFT structure by using these two equations. And this equation too can also be written in an alternate form where you can replace this total factor wnk plus n by 2 by negative times of wnk. That equation is also correct, but we will use these two equations in this lecture. And these are the total factors which we have calculated in the previous lecture. These total factors will be used in the radix to FFT structure. So let's see how we can implement a radix to FFT structure for 8-point DFT. So we are going to discuss an implementation of 8-point FFT with the help of two 4-point DFTs. Now let's start implementing the FFT structure from the beginning. Here, as you can see, we have split an 8-point sequence into two sequences where each sequence contains 4 samples. So the index values are 0, 1, 2, 3 in each case. Now we are going to take 4-point DFT of both sequences, and each 4-point DFT will produce 4 samples at its output, which can be considered as A0, A1, A2, A3. So A of K will represent the first 4-point DFT outputs. Similarly, the output samples of the second 4-point DFT can be considered as B of 0, B of 1, B of 2 or B of 3. So B of K will represent the second 4-point DFT outputs. Now our task is, with the help of these two 4-point DFT outputs, we have to construct the overall or a single 8-point DFT output. And the thing to remember is that to calculate every single frequency domain output, we have to add two samples. One sample coming from the first 4-point DFT and the other sample coming from the second 4-point DFT. So let's start with x of 0 and x of 4. To calculate x of 0, we will need a of 0, which is this sample, and b of 0, which is this sample. So in order to get the result of x of 0, we have to add a of 0 with b of 0. So we have to draw a line from this point to this point so that we can add b of 0 with a of 0. Similarly, in order to calculate x of 4, we will need again a of 0 and b of 0. So this is the b of 0 sample and this is the a of 0 sample. So we again need to draw a line from this point to this point so that we can send the value of a of 0 to this point. So in this particular way, we can add a of 0 with b of 0. Similarly, to calculate x of 4, we can add a of 0 sample with b of 0 sample. But please remember that before addition of these two samples, in both cases, we have to multiply the total factor values, which are not mentioned here. Basically, we will mark all the total factors at the end for all the 8-point DFT outputs. Now let's see how we can calculate x of 1 and x of 5. In order to find x of 1, we have to add a of 1 and b of 1. So this is a of 1 sample, which is shown here as in a straight line, and b of 1 is this sample. So we have to draw a line from this point to this point so that we can add both the samples, and the junction of two arrows shows the addition operation. Similarly, in order to find x of 5, we again need a of 1 and b of 1. So b of 1 is this sample, which is shown as a straight line here, and we have to draw a line from this point to this point in order to use a of 1 sample here for addition purpose. Here I have just put k is equal to 1 in equation 1 and 2, which was discussed earlier. Now let's come to the x of 2 and x of 6 output. To calculate x of 2 and x of 6, we have to put k is equal to 2 in equation 1 and 2, which was discussed at the start of lecture. So in order to find x of 2, we have to add a of 2 with b of 2. So a of 2 is this sample, which is shown as a straight line, and b of 2 is this sample, which we have to use here. So we will draw a diagonal line like this one. Similarly, in order to calculate x of 6, we again need a of 2 and b of 2, which we will add them after multiplication with total factors. So this A of 2 sample will be sent here as in the form of diagonal line, and B of 2 sample will be used here as a straight line. Now let's come to the x of 3 and x of 7 output. To calculate x of 3 and x of 7, we have to combine the last sample of both the 4-point DFT outputs. So in order to find x of 3, we have to add a of 3 and b of 3. So a of 3, which is the last sample of the first 4-point DFT, is this one, which is shown by a straight line. And b of 3 is here, which is the last sample of the second 4-point DFT. So we will draw a diagonal line so that we can use b of 3 for an addition operation. Similar is the case for x of 7. We again need a of 3 and b of 3. So b of 3 is this one, which is shown by a straight line. And in order to use a of 3 during addition, we will draw a diagonal line from this point to this point. So this is how we can combine two 4-point DFT outputs in order to make a single 8-point DFT output. But here, as you can see, we have not marked twiddle factors yet. In order to calculate a single frequency domain coefficient value, we will need a single twiddle factor value. For example, for x of 0, we will need W80 twiddle factor value. For x of 1, we will need W81. Why we are using the substitute value equal to 8? Because it is the case of 8-point DFT. So W80 will help us to calculate the DC harmonic value. W81 will provide the fundamental harmonic value. W82 will be used during the calculation of x of 2. W83 will be used in the calculation of x of 3. Similarly, W84, W85, W86, W87 will be used during the calculation of x of 4, x of 5, x of 6 and x of 7 respectively. Now the question is, at what particular position we have to mark the twiddle factors? The key concept is that we have to multiply twiddle factors with the second 4-point DFT output values. No multiplication will be done with the first 4-point DFT output samples. So this is the key rule which you should remember while marking the twiddle factors values. So let's see how we can mark those twiddle factor values in this structure. Okay, here as you can see, for every single frequency domain output value, we are adding two samples. One sample is coming from the first 4-point DFT box, while the second sample is coming from the second 4-point DFT box. And twiddle factors are required to multiply with those samples which are coming from the second 4-point DFT box. So let's start with x of 0. In x of 0, we are adding a of 0 and b of 0. So b of 0 will be multiplied with W80 before adding with a of 0. Similarly, for x of 1, we will add a of 1 and b of 1 will be multiplied with W81 before addition with a of 1. So W81 will be marked right here. Similarly, for x of 2, this sample is coming from the first 4-point DFT box, so no multiplication will be done here. While the second sample, which is coming from the second 4-point DFT box, will be first multiplied with W82 and then it will add in the a of 2 sample value. Similarly, for x of 3, a of 3 will appear as it is, while b of 3 will be first multiplied with W83 twiddle factor and then it will add with a of 3 sample in order to produce x of 3. So the conclusion is, for the first 4 sample values of the 8-point DFT output, twiddle factors will be marked on the 4 diagonal lines because these diagonal lines are coming from the second 4-point DFT box. Now let's come to the last or the remaining 4 sample values of the 8-point DFT output. For x of 4, we are adding again 2 samples. One sample is coming from the first 4-point DFT box, while the second sample is coming from the second 4-point DFT box. So again, the multiplication of twiddle factors rule will remain same. We have to multiply twiddle factors with those samples which are coming from the second 4-point DFT box. So B of 0 sample will be first multiplied with W84 and then we will add it with A of 0 which is coming from the first 4-point DFT box. So A of 0 will appear as it is while B of 0 will be first multiplied with W80 before addition. Similarly for X of 5 we are adding two samples. First sample is coming from the first 4-point DFT box while the second sample is coming from the second 4-point DFT box. So this sample will be first multiplied with W85 and then we will add them. Similarly for X of 6 we are adding two samples. The first sample is this one which will appear as it is while the second sample will be first multiplied with W86 and then we will combine them. And lastly for X of 7 again we are adding two samples. The first sample is this one which will appear as it is while this sample or the second sample which is coming from this 4-point DFT box will be multiplied with W87 and then we will add them. So the conclusion is for the last or for the remaining 4 frequency domain sample values we will multiply total factors on these 4 straight lines because these straight lines are actually coming from the second 4-point DFT box. So this is how we can implement an 8-point radix to FFT structure when we are using two 4-point DFTs. Now let's think about these two sequences where each sequence contains 4 samples. If we will split these two sequences into further two sequences of equal length, then what will happen? We can make two sequences containing odd index values and even index values. So the first sequence will contain this sample value which is present at 0 index and this sample value which is present at 2 index. So the first sequence will contain X of 0 and X of 4 while the second sequence will contain the odd index values which are 1 and 3 index values. So the second sequence will contain X of 2 and X of 6. Similarly, if you will split this sequence into two sequences containing even and odd index sample values respectively, then the first sequence will contain X of 1 and X of 5 while the second sequence will contain X of 3 and X of 7. So let's see how we can implement 8-point FFT structure using these 4 2-point DFTs.